Hello there, space traveler. Tonight the cabin lights are low and the sky is wide open. We will explore the most revolutionary project that the scientific community has been working on. At least that is the promise of this century for space exploration, and that is the project Breakthrough Starshot, a project that aims to send nanoships to nearby solar systems that might harbor life. Traveling by conventional means, such as rockets, could take up to 10 million years. The idea is simple: to propel these tiny ships using the pressure of powerful lasers, similar to how a sailboat uses wind to move. And the most incredible thing is that the journey would take only 20 years to reach the solar system like Alpha Centauri, which contains planets within the habitable zone of life. We could deploy these miniature vessels equipped with cameras and high-frequency antennas for communication. First things first, drop a comment below and tell me, if you could send a tiny probe anywhere in the galaxy, where would you want it to go? And let me know what time it is for you right now. If you enjoy this cosmic adventure, hitting like and subscribing truly helps us bring more space science to everyone. Now, let's set the scene. Turn down the lights, settle in somewhere comfortable, and let your tension melt away with a deep breath. Find a spot free of distractions, and don't worry if sleep catches up before the video ends. This voyage is gentle, and the story will be waiting for you when you wake. Imagine the familiar arc of a launch. A pillar of fire, a slow lean, the blue thinning into black. Rockets are spectacular at leaving a planet. They are less gifted at crossing a light year. The reason is not a lack of courage or metallurgy. It is the arithmetic that binds any vehicle carrying its own fuel. In the quiet language of motion, that arithmetic is written by the rocket equation. The speed a rocket can gain depends on how fast it throws mass backward and how much of itself it is willing to throw. On Earth, this is a triumph stage after stage dropping away, the last engine lighting, orbit captured. But stretch the destination to 4¼ light years, and the same arithmetic becomes a kind of gravity of its own, pulling dreams back toward realism. The fuel problem is not only that fuel is heavy, it is that pushing fuel requires more fuel. Every kilogram you add so you can go faster demands more kilograms to push that kilogram, and so on, a spiral that races upward far faster than intuition. Chemical propellants hurl exhaust at a few kilometers per second. Even the best oxygen-hydrogen engines toss it at roughly 4½. If you want the ship's speed change to be a large fraction of the exhaust speed, the mass of propellant must dwarf the mass of the ship. For interstellar hopes, where the desired speed is not a few kilometers per second, but tens of thousands, or even a fraction of light, this trade becomes brutal. Add stages, and you gain breathing room for orbit or for Mars. Add 1,000 stages in your imagination, and the payload vanishes into tanks. More efficient engines exist in principle and in practice. Nuclear thermal rockets heat hydrogen and throw it faster, perhaps twice the exhaust speed of chemical engines. Electric and ion engines do better still, accelerating ions to tens of kilometers per second with exquisite thrift, sipping propellant to produce a steady, gentle push. These are beautiful tools for the inner solar system and beyond, when time is measured in months and years. But ion thrusters need electrical power, and power sources have mass. Their thrust is as soft as a feather. They cannot, by themselves, fling a ship to a fifth of light speed in any reasonable span. Imagine a candle pushing a sailboat across an ocean. Given enough time and no storms, it might nudge the hull forward. But continents are patient in a way people and programs are not. Even if an engine could sustain thrust for years, energy itself draws a hard line. To take a modest mass to a truly interstellar speed requires an astonishing budget. At 20% of light speed, the kinetic energy of even a gram becomes fierce. Scale the mass up to a human craft, and the energy climbs beyond the comfortable reach of anything we can hope to launch. And that is only for speeding up. If you wish to stop near the destination, to orbit a new sun, to loiter where a planet waits, you must pay the energy debt again in reverse, or carry a scheme for braking that does not rely on propellant. The bill doubles, and the rocket equation tightens its grip. Travel time anchors the imagination to numbers. The fastest probes we have sent out, Parker Solar Probe grazing the sun's fire, Voyager coasting beyond the heliosphere, move at tens of kilometers per second. At those speeds, Proxima Centauri is not decades away, but tens of thousands of years distant. Improve the speed tenfold, and the calendar is still measured in millennia. This is not failure. It is a faithful report from the scale of space. Light needs a little more than 4 years to make the crossing. A ship that settles for 1% of light speed still takes 4 centuries. Human lives, budgets, and attention are not well matched to such spans. To bring the journey into decades rather than eras, the ship must touch speeds no rocket has ever delivered. There is a subtler barrier that hides inside staging diagrams and propellant charts. Rockets work best when they can trade mass for speed in a place where gravity is strong and time matters, launching from a planet, capturing into orbit, hopping between wells. Interstellar space is not like that. Between stars there is almost nothing to push against, no air to scoop, no fuel to refuel, no harbor to take shelter in. A rocket that tries to carry what it needs for both acceleration and braking becomes a warehouse with engines, and the warehouse must be pushed by what it carries inside. The circle never closes elegantly. Concepts that harvest interstellar hydrogen to burn in fusion engines have been sketched on paper and loved in novels. But the interstellar medium is thin and unruly, and fusion itself has not yet been made a tame ship's stove, even on Earth. It is tempting to say, perhaps we should wait for the perfect engine fusion ignited at will, antimatter bottled like lightning, something beyond the zoo of today's designs. Waiting can be wise. It keeps us from building monuments to wishful thinking. But waiting can also become a way to never begin. And in the meantime, physics is offering a gentler redirection. If carrying fuel traps us in an exponential penalty, perhaps we should not carry fuel. Perhaps we should let the energy source stay at home, where mass and maintenance are manageable, and let the ship be small, clean, and almost empty. Perhaps we should push not by throwing mass backward, but by letting light itself do the pushing. That thought changes the shape of the problem without pretending the distances are smaller. Photons, the quanta of light, have no rest mass, but they carry momentum. When they reflect from a mirror, they give up twice their momentum to the surface. A tiny shove that is honest and accumulates. Sunlight provides this shove freely. Lasers can provide it in torrents on command. A sail that is large and shiny and feather-light can feel that pressure and move. Nothing is burned. Nothing is thrown away. The penalty for carrying fuel evaporates. The cost moves elsewhere, into materials thin enough to float on light without cooking, into beams coherent enough to stay tight and true, into guidance that can ride a column of photons like a coin balanced on its edge. Rockets remain our ferries to orbit and our freighters for worlds close enough to reach with patience. They always will. Their limits are not a condemnation. They are the outline of what they do best. But for the space between stars, the arithmetic they obey asks us to look sideways. The way forward is to decouple the engine from the traveler, to let the traveler be almost nothing but sensors and sail, and to keep the engine planted vast, heavy, and tended close to home. That is the hinge where this story turns, from tanks and exhaust to mirrors and beams, from carrying fire to catching light. In the next chapter, the sail itself will unfold, first under the sun's soft hand, then under a man-made wind bright enough to turn minutes into a launch and decades into a crossing. Settle in and picture a quiet bay at dusk. A sailboat moves without fuss because the air, full of tiny molecules you cannot see, presses against a stretched sheet of fabric. The sail gives that invisible wind a broad surface to push on, and the hull turns that push into steady motion. It's simple, almost gentle. Now lift that picture out of the water and place it in space, where there is no air at all, no molecules, no breeze, nothing to lean on. The old trick shouldn't work anymore. And yet, something else is flowing there all the time. Sunlight. Light does not have mass, but each photon carries a whisper of momentum. When billions upon billions of those photons strike a surface and bounce, they leave behind an honest, tiny shove. That is enough to sail on. A solar sail is not canvas. It is a mirror made from film so thin it rustles at a breath. The job is not to catch wind, but to reflect light as perfectly as we can. Reflection matters because absorbing light turns energy into heat. Reflecting, it lets the sail keep its cool and doubles the push. Sunlight's pressure is faint far lighter than a feather spread across a table, so the sail must be wide and the spacecraft must be small. Think of the craft not as a bus hauling fuel, but as a modest box of brains, and sensors about the size of a household microwave, held at the center of a gleaming square far larger than itself. The ratio is the point. Area gathers the photons. Low mass lets that gentle pressure matter. You don't have to take this on faith. NASA is already practicing the language. A mission called a CS-3 launches compact, then opens a sail of roughly 80 square meters, once it as free of the atmosphere, about the footprint of 6 car parking spaces laid side by side. The bus is small, the sail is large, and sunlight does the work. Nothing burns. Nothing runs out. The acceleration is slow enough to be invisible in a moment and decisive over months. a steady add-up that turns patience into speed. Engineers watch how the sail unfolds, how it keeps its shape, and how slight changes in angle can steer a path without spending propellant. Steering is an art of posture. On the ocean, you can tack across the wind, using the keel's bite to turn sideways pressure into forward motion. In space, there is no keel, but there is geometry. By tilting the mirror just a few degrees off the line to the sun, a sailor of light can trade a little outward push for a gentle sideways drift, spiraling inward or outward from the star. Trim tabs, tiny shifting masses, or smart coatings that change their reflectivity with angle can hold that posture without waste. The craft behaves less like a rocket and more like a kite in a permanent, invisible breeze. The hard part is easy to say and demanding to build. Very large, very light, very shiny, and very calm. The film must be thin enough that a square meter weighs almost nothing, bright enough to reflect nearly everything that hits it, and tough enough to shrug off heat, cold, and the sharp edges of sunlight. The booms must unfold cleanly and hold the sheet flat. A wrinkle here, a tear there, and the pressure becomes uneven. The sail tilts or tumbles. None of this is magic. Its careful materials work composites for stiffness, nanometer metals for reflectivity, polymer films measured in micrometers, and it gets better with practice. Because the push is gentle, the dream grows with area. The same teams that learn on tens of square meters are already sketching sails of hundreds, then thousands. 2,000 square meters on the order of half a football field sounds extravagant until you remember how soft the sunlight's hand really is. That size is what turns a whisper into a steady nudge for a featherweight craft. The bus at the center stays modest because it has to, power scale to the task, radios trimmed to a realistic link, sensors chosen for thrift. The ship grows by subtraction, less mass, more mirror, and the mirror does the rest. There are limits here, and they're honest ones. Sunlight alone will not fling a sail to a neighboring star in a tidy span of years. It is perfect for lingering missions, for patient climbs and long arcs around our own sun, for journeys where running out of fuel would have ended the story. It teaches us how to fold and unfold, how to hold shape, how to steer with light instead of fire. And that practice is exactly what we need before we dare to ride a man-made wind. Because the same physics that lets a sail lean against sunlight will let a much smaller, tougher sail lean against something. Brighter a stadium of lasers aimed from Earth for a few intense minutes, turning a slow walk into a sprint and a long voyage into a human-length wait. For now, keep the picture close. A mirror as wide as a room, a little box at its heart, the sun at its back, and a path carved by photons that never tire. That's the alternative to tanks and exhaust motion written in light, and it's the stepping stone to the stronger push we'll call on next. Breakthrough Starshot is a research program rather than a single scheduled mission, a long, careful attempt to answer one focused question. Can a fleet of gram-scale spacecraft, each no larger than a coin and riding an ultralight mirror, be pushed from near-Earth space to roughly a fifth of light speed by a man-made beam of light? coast for decades through the interstellar dark, and send back a whisper of data from the neighborhood of Alpha Centauri? It is a bet on beamed propulsion, on leaving all the heavy energy hardware at home, and letting the traveler be almost nothing but sensor and sail. The promise is stark in its simplicity. If the push can be delivered in a burst that lasts minutes rather than months, the cruise that follows fits within a human lifetime. If the hardware on the ground can be reused, attempts can be repeated until statistics begin to favor success. If the sail can survive heat and stress and stay balanced on the center of the beam, momentum does the rest. Breakthrough Starshot is not a single launch date circled on a calendar. It is a focused research effort built around one stark idea: leave all the heavy energy hardware on Earth. Make the spacecraft almost nothing but a mirror and a mind, and push it to interstellar speed with a brief, disciplined blast of light. The destination that concentrates attention is the Alpha Centauri system, close by in galactic terms and scientifically irresistible. The vehicle is a wafer of electronics about the size of a coin, close to 1 gram in mass, wrapped in an ultralight sail engineered to reflect nearly everything that touches it. The promise lives in the timing. If the push can happen in minutes rather than months, the cruise that follows fits inside a working lifetime, and the data can return before the generation that launched the attempt is gone. The spacecraft feels small on purpose. A thumbnail camera, a star tracker, a clock, radiation-tolerant logic, and a sliver of memory share a single chip. Around that core sits a sail, measured in hundreds of nanometers of thickness. More optical component than fabric, its layers tuned the way a lens is tuned, rather than woven the way cloth is woven. Propellant tanks, feed lines, and engine bells are absent by design. What provides momentum is the beam that stays at home. That beam is built from many modest lasers acting as one. Thousands of emitters are tiled into a phased array so their wavefronts line up, crest on crest, trough on trough, and add into a single column. The array does not swivel like a cannon. It steers by adjusting phase, nudging the timing of each element so the combined light leans through the sky. Between ground and space, the atmosphere shimmers, bending and blurring the wavefront. Adaptive optics sense that shimmer and cancel it in real time, the same way a modern observatory sharpens starlight into a steady point. When the path above is clear and safe, the array concentrates a narrow, coherent shaft of photons and sends it upward. That shaft is the wind. Performance targets are plain. A cruise near 1/5 the speed of light, roughly 60,000 kilometers per second, means a 1 gram craft must reach that speed in about 2 minutes of push. The average acceleration is on the order of 60,000 times Earth's gravity. The force arrives as pressure spread across a sheet that weighs almost nothing, which is kinder than a sudden jerk. But the sail must keep its shape under that load. Edges cannot fray, seams cannot snag. A ripple that would be harmless at low acceleration becomes a tumble that ends the attempt before it begins. Thermal limits set the next rule and admit no negotiation. Under a man-made sun, absorbing even a few parts per million of the beam's power will heat a film this thin faster than it can cool to space. Survival demands reflectivity around 5 nines, about 99.999%. So nearly every photon is returned to the beam, and almost none become heat. The surface must do two jobs at once: behave like a near-perfect mirror at the laser's color, and behave like a near-perfect radiator in the thermal infrared, so the tiny fraction of absorbed energy can leak away. This is why the sail is a metasurface. Layers and patterns below the wavelength of light control, the phase of the reflected wavefront, and the spectrum of emitted heat. Dielectric stacks, high melting point ceramics, perhaps diamond-like carbon materials are chosen not for romance, but for absorption coefficients, emissivity, and strength at temperature. Stability is earned by geometry rather than muscle. Beams have edges, hardware jitters. Sails see tiny tilts. A shallow conical or gently cupped profile turns the beam into a bowl. Drift off center, and pressure grows on the nearer side, nudging the sail back toward the axis. A slow spin adds gyroscopic calm without fighting guidance. Along the rim, small features can make reflectivity vary with angle, so a slight tilt generates a restoring torque. No propellant is spent on this balance. The shape itself prefers the center line and rides there. The sequence unfolds quickly. A carrier in high orbit releases the folded sail and moves away. Booms extend, the film pulls flat, and a curved figure locks into tension. The wafer checks its pose against the star field and sends one last clean report. On the ground, the array draws from storage, phase locks its tiles, confirms that aircraft and satellites are clear, and touches the sail with a soft first press so the craft can settle on the column. Telemetry fades no gram-scale radio can shout through that glare. Power rises along a profile, vetted by the sail's thermal model. The wavefront stays flat, the restoring shape holds. The minutes pass, the beam dims. Then it is gone. Silence returns as if nothing had happened, except that something has. A gram and a mirror have become the fastest human-made object that has ever existed. After cutoff, the vehicle changes posture for the long crossing. The sail turns edge-on to sunlight and stray photons, or it is repurposed as a shield so the wafer can ride in its shadow. The star tracker builds a new map and holds it, waking on schedule to check attitude and make hair-thin corrections using photon torques or tiny actuators. There is no propellant for big course changes. Navigation is patience and geometry. The clock advances. Power is rationed. Memory is checked and rechecked against radiation upsets, and the craft becomes what the plan intended: a stone thrown well. Interstellar space is thin, but not empty. At 1/5 the speed of light, a dust grain carries enough energy to pit, crack, or kill. Risk is managed in layers. The sail remnant can serve as a bumper. The wafer's leading edges can be shaped to glance blows instead of catching them. And the mission is distributed across many craft rather than entrusted to one. Some will fail at deployment. Some will overheat at a hot spot where absorption was a little too high. Some will drift off the beam before the full push. And later, some will be salted by a grain at the wrong moment, or numbed by a single particle that flips a critical bit. A swarm trades the illusion of certainty for usable odds. If hundreds or thousands are sent, a fraction will survive the minutes, and a smaller fraction will survive the decades, and the chance that at least one passes the right corridor near Proxima b becomes a number a sober team can plan around. All of this rests on infrastructure that is recognizable rather than mystical. A phased array large enough to matter sits on high, dry ground to minimize atmospheric absorption and turbulence. Grid-scale storage charges slowly and discharges quickly to feed the 2-minute pulse. Safety is designed in shutters that fail dark, interlocks that watch air and orbital traffic, rules that keep the beam inside its corridor, or not on at all. The array can fire again and again. The manufacturing line can stamp out new wafers and new sales. The experiment repeats until the statistics turn. The demands, when taken together, are severe but legible, reflect nearly everything at the laser's color, or overheat, hold shape under roughly 60,000 G or tier, keep the beam flat, tight, and steady for about 2 minutes, or wander out of the lane. Build passive stability into the sail so it prefers the center of the column, or spend any control margin in seconds. None of these demands ask for a new law of physics. All of them ask existing disciplines, materials science, photonics, control, energy systems to stretch. When a requirement resists, schedules slip and prototypes change. The premise does not evaporate. What follows from a successful push is a mission measured in quiet. The wafer coasts through a long, cold room between stars, checks its attitude against the same sparse constellations, and waits for a timed rendezvous with a narrow corridor near a neighboring sun. If timing and targeting hold, sensors wake at the right moment for a fast glance imaging, spectra, light curves squeezed into seconds, and then the craft turns its tiny aperture toward home and begins to send. The signal will be a whisper aimed at an ear spread across the Earth, a receiver array that adds many small instruments into one, pulling bits from noise with coding and patience. The scale is human at both ends, a field of lasers used in minutes and years of listening to catch the answer. If a single shard returns a crescent, a phase curve a spectrum with a line that hints at an atmosphere, that will be enough to show that light can be both engine and story, that minutes of fury can buy decades of drift, and that a gram of intention can cross the first step to the stars. Announced in 2016 under the Breakthrough banner, Starshot set a single audacious objective and refused to decorate it. Develop the tools to push. Gram-scale spacecraft to roughly 20% of light speed and aim them toward the Alpha Centauri. System for a fast flyby and a data return. No colony ship, no decades of continuous thrust, just minutes of disciplined push from Earth, followed by decades of quiet coasting through interstellar dark, and then a brief, carefully timed glance at another sun's neighborhood. Everything else in the program serves that narrow aim. The architecture is deliberately asymmetric. Heavy, complex, maintainable hardware stays at home. The traveler remains simple, small, and almost empty. On the ground, a phased array of many modest lasers acts as one instrument, shaping and steering a coherent beam through the atmosphere with adaptive optics and strict safety gates. In space, a tiny wafer of electronics camera, clock, star tracker, memory rides at the center of an ultralight, highly reflective sail, tuned more like an optical component than a fabric. A carrier in high orbit releases one sail at a time. The array delivers a pulse on the order of 2 minutes. The sail reaches cruise, and the rest of the mission becomes patience and navigation. Goals were framed with uncommon precision. First, demonstrate that a sail measured in hundreds of nanometers of thickness can reflect nearly all incident power at the beam's wavelength, while shedding the trace of absorbed heat, mirroring at the laser color, and radiating strongly in the thermal infrared. Second, prove passive beam riding stability by geometry, rather than by expending propellant. A shallow conical or cupped profile, perhaps a gentle spin, trim features that create restoring torque's when the sail drifts off-center. Third, show phase-locked operation of large laser tiles through moving air, including wavefront sensing and correction fast enough to keep the synthetic aperture flat for the full pulse. Fourth, build a wafer-class payload that survives roughly 60,000 G at launch, endures decades of radiation and dust hits, and still wakes on schedule to aim sensors and a needle-thin downlink toward Earth. And finally, rehearse the mission concept end-to-end with pathfinders, deployment mechanics, beam tests at small scale, cislunar and heliocentric dress rehearsals that trade speed for confidence. Ambition drew skepticism immediately, and the program's own documents acknowledged why. Reflectivity at the 5 nines level, about 99.99%, is not an incremental polish. It is a materials problem at the limits of absorption and emissivity. Beam coherence across thousands of emitters through turbulent air demands control systems that behave like a large observatory running in reverse. The acceleration environment is alien to most flight hardware. Anything that can snag, ripple, or delaminate will. And even perfect launch leaves a long crossing in a medium that is not truly empty. A single dust grain at 1/5 of light speed carries enough energy to scar or silence a sensor. Starshot's answer to each of these concerns was practical rather than rhetorical. Break the problem into laboratories and testbeds, work each gate independently, and measure progress not in slogans, but in samples, tiles, control loops, and deployment videos that either behave or don't. The mission profile was set early and has stayed plain. There is no braking at Alpha Centauri. Nothing in the vehicle's mass budget can pay that energy debt. The plan is a high-speed flyby aimed to pass within a useful range of targets of opportunity Proxima b, if geometry allows. Other members of the system, if they offer a clearer corridor, and a rapid sequence of measurements, imaging across a handful of filters, a spectrum or two, where the signal permits. A light curve precise enough to notice phase and scattering. The return is radio, not laser, because the craft cannot carry a deep space laser transmitter. The downlink leans on coding, long integrations, and a receiver array on Earth that acts like one ear spread across many dishes. It is not graceful, but it is honest. The physics of distance and power set the rules. Time horizons were never advertised as short. The early work belongs to materials science and photonics metasurface stacks that refuse to heat under harsh illumination. Dielectric layers that hold phase while remaining mechanically calm. Phased array tiles that keep their timing when the wind shifts. Energy storage that can fill steadily and discharge like a sprint, shutter systems that fail dark. The middle work belongs to system integration, turning lab samples into deployable sails, turning benchtop coherence into outdoor coherence, building safing, tracking, and governance, so a multi-gigawatt instrument can only operate inside a clean corridor. The late work belongs to flight, small on-orbit push tests to validate beam riding physics, then longer flights that trade peak acceleration for duration, then a first complete attempt when every prior gate has been closed. Even in success, the calendar is unhurried. Minutes of fury at the start, 20+ years of cruise, 4+ years for the first photons to come home. Because the outcome is uncertain, the program made room for value along the way. A phased laser array that can write and hold a coherent wavefront through air is also a power beaming platform, a precision test bed for optical communications, and a tool for atmospheric science. Sail materials that survive extreme flux with almost no absorption will matter in thermal management and photonics far from spaceflight. Wafer-class spacecraft that tolerate violent acceleration and then operate autonomously for decades teach lessons that flow back into small planetary probes, heliophysics, and even Earth observation. Even the ground receiver network required to catch a whisper from 4 light years away looks a lot like infrastructure valuable to both radio astronomy and technosignature searches. The project's posture stays consistent. Narrow scope, hard gates, repeated attempts. The beam is infrastructure that can fire again and again. The vehicles are inexpensive enough, once learned, to fly in swarms. Statistics stand in for guarantees. A small fraction will survive the launch. A smaller fraction will survive the crossing. With enough tries, at least one may pass a target at the right distance and angle to see something that changes what we know. If the tests stall, if reflectivity does not reach the needed purity, if wavefront control refuses to scale, if safety rules cannot be met in practice, the program still leaves behind better optics, better materials, and better small spacecraft. If they do not stall, a gram-scale traveler will one day look sideways at another sun, capture seconds of truth, and begin to send them home. The beam has already faded. A wafer and its mirror have held together for the full profile, and the trajectory that follows cannot be caught. What now unfolds is the promise left hanging a moment ago. Seconds of truth at a neighboring sun, earned by a mission that spends its courage in minutes and its patience in decades. The handoff from ground to deep space begins immediately, quiet and exact, because everything that matters later depends on what is done in the first calm breaths after the push. The sail no longer needs to behave like a wing. It becomes shade, shield, or ballast. Edge-on posture trims the cross-section to stray light and dust. If structure allows, the film rides forward as a bumper, so the wafer can hide in its shadow. A prepared star field fills the tracker. The attitude solution locks. The first tick lands on a decades-long navigation plan that uses geometry instead of propellant. From that moment, guidance is a rhythm of small acts done well. Clocks advance on schedule, sensors wake sparingly. Memory is scrubbed for radiation upsets, and attitude is trimmed by photon torques on vanes or by tiny actuators that tilt surfaces by fractions of a degree. Prediction carries more weight than correction. Stars shift with proper motion. A target system does not wait where it was. At a fifth of light speed, the sky itself squeezes forward under relativistic aberration. Tables carried from home describe what the tracker should see month by month. When reality and tables agree, the craft coasts. When they drift, millidegree adjustments restore the match and the craft waits again. Navigation becomes a calendar you can trust. Power is a ledger with no windfall entries. Thin films harvest what they can. Storage is sized for long sleeps and brief, bright tasks. Detectors live in permanent shade, tied radiatively to deep space rather than cooled by expendables. Every watt that is not spent now is a watt that can be spent when the corridor tightens and single frames matter. There is almost nothing to heat and almost nothing to cool, but almost nothing still demands discipline. The medium between stars is thin and unforgiving. At cruise, an atom strikes like a soft bullet. A dust grain strikes like a chisel. Defense begins with posture. Leading edges are chamfered to glance blows. Sensitive surfaces live in the lee of sacrificial layers. A remnant of the sail, if it remains, takes the worst of the pitting while the wafer endures. The rest is statistics. No single traveler can guarantee a clear lane. A dispersed set on slightly different tracks gives the mission a chance to find one. Swarms replace flagships because reliability at this scale is earned in numbers. A lone immaculate craft must be perfect through deployment, beam ride, cruise, and encounter. A flock of simple craft can fail many times and still deliver one success. Progress is measured in firings rather than launches, in films that survive longer this month than last, in fans of trajectories that cover uncertainty in the target's position and motion. If a few percent finish the push and a smaller percent finish the crossing, the probability that at least one passes the right corridor near Proxima B becomes a number you can plan against. Time refuses shortcuts. At roughly 0.2 C, Alpha Centauri is still a decades-long crossing. Light itself needs a little more than 4 years to bring the first answers home after the encounter. Time dilation exists at that speed, but stays small. Clocks aboard and clocks on Earth drift by only a few percent over the cruise. The consequence is practical, not paradoxical. Instruments must age slowly, software must carry its own care, and ground teams must hand a baton across generations without losing the thread. Approach compresses everything. A system the size of our inner solar system is crossed in minutes. A world's useful angular size swells and fades within tens of seconds. Imaging and spectroscopy prepare for motion blur and hard phase angles. Very short exposures, burst capture, predictive pointing that leads the target by a calculated offset, and deconvolution on the ground that uses the known motion to recover detail. Any cruise spin is halted or adjusted, so sensors stare in the plane of closest approach at the right instant. There will not be another pass. Transmission begins as soon as geometry allows. A tight, low-power signal is aimed toward Earth, coded to survive noise and repeated without drama. The receiver is not a single great ear, but many smaller ones summed across continents. An interferometric net that lifts bits out of background by patience rather than volume. The delay is fixed by nature. Even in success, the first fragments gathered near Proxima will not arrive for a little more than 4 years. The data are ordered accordingly, most precious first. Acknowledgements when they can be afforded. Repeats when silence suggests loss rather than completion. The long drift is not empty. Health beacons confirm survival and tune the ground array that will one day listen for science. Starfield snapshots refine the aim for the final corridor. Occasional crossings of a dust sheet of a faint tail provide calibration scenes at the edge of detectability. Each small success buys margin for the only minutes that truly matter. This operating mode, minutes of fury, decades of quiet, does not soften the physics. It rearranges the work. Energy is spent in a pulse at home. Time is spent in the dark between suns. Information is rationed and then released when the sky opens for seconds and closes again. Where rockets carry their risk in tanks and plumbing, beamed sails carry theirs in mirrors and pointing, and then hand the rest to patience and statistics. If the pieces hold, if the tables stay honest, if the trims stay small, if the crossing stays kind, those promised seconds of truth become a picture. A spectrum, a light curve with structure and the first. Reply takes shape on a patient screen far from where the beam first lit. The sail has to serve as mirror, shield, and gyroscope at once, and each roll pulls the design in a different direction. As a mirror, it must return almost every photon to the beam without keeping the heat. As a shield, it must keep its skin intact when dust grains strike at 1/5 of light speed and when beam irregularities try to bruise it with hot spots. As a gyroscope, it must hold posture without spending propellant, riding the center of the beam with a preference for balance rather than a need for constant correction. All of that lives inside a film measured in hundreds of nanometers thinner than a smear of smoke stretched to dimensions that look extravagant next to a 1-gram payload. The mirror part begins with a stack of layers, so thin the wavelength of light can count them. Metasurface is the word often used. A surface pattern below the scale of the laser's color, so it can tune the phase of the reflected wavefront, not just bounce light like kitchen foil. High-index and low-index dielectrics materials that barely absorb the chosen. Wavelength alternate in nanometer sheets to form a Bragg reflector that throws the beam back cleanly. The topmost skin must shrug at the laser's color, while the deeper layers help in a different band, the thermal infrared. Whatever small fraction of light is absorbed must be able to leave as heat. The sail wants high emissivity where it cools and near-perfect reflectivity where it is pushed. That is a hard combination, and it shows up in the material choices. Thin oxides and nitrides that keep absorption coefficients near zero at the laser's color. Ceramics that do not soften when warm, and engineered interfaces that do not delaminate when the stack flexes. Thickness matters because mass matters, but thickness also matters because the internal temperature field must not concentrate. A sail with poor in-plane thermal conductivity will let a single, bright speck grow hot faster than it can share the heat with its neighbors. In-plane heat spreaders, tucked below the optical surface ultra-thin ceramic networks, diamond-like films that conduct heat laterally without drinking the beam flatten those gradients. The surface texture itself has to avoid field intensification. Sharp sub-wavelength edges can turn a flat wave into a patchy one and invite local absorption. The safest mirror is smooth in the language of light and rough in the language of heat. No optical corners where hot spots can begin, but plenty of microscopic paths for warmth to find the night. Shape earns stability. A perfectly flat square at the center of a perfectly flat beam is a textbook sketch, not an experiment. Real beams have a profile. Real air adds microjitter. Real films wrinkle and breathe. The sail, therefore, carries curvature on purpose. A shallow conical or gently cupped form that feels more pressure where it wanders, pushing itself back toward the axis like a marble settling in a bowl. That curvature does double duty. It lifts the center of pressure to sit above, or just where we want it with respect to the center of mass, so that a small tilt creates a restoring torque. A slow spin adds gyroscopic calm and pulls the film into tension, ironing small wrinkles that would otherwise grow into flutter. Spin cannot be a crutch. The beam still has to be ridden by geometry, but centrifugal tension turns a delicate sheet into a drumhead that prefers to stay true. Edges and seams are the places where a design tells the truth about itself. A seam is a line of risk. It diffracts light. It invites a crack to begin. It provides a different path for heat. The best version of a large sail is not a quilt of coarse tiles, but a field of sub-wavelength stitches where the optical phase stays, continuous across joins, and the mechanical load spreads without a single thread bearing too much. Ripstop microgrids can be built into the film at scales smaller than the beam's features, so a tear arrests itself before it can race across a quadrant. Curvilinear reinforcement arcs, rather than straight spoke shifts, stress away from corners and discourages straight-line rips. Even the fold pattern for launch is a material choice. A crease is a memory. If it is set wrong, the film will try to remember it under load. Origami that distributes bend angles over many tiny radii lets the sail unfold without a permanent scar. Micrometeoroids and dust are not a shower. They are a life support problem. At the speeds in question, a grain that would be harmless at walking pace carries energy like a rifle shot. The answer is not armor is mass, but layering and posture. A sacrificial topcoat can spall, vaporize, and carry the worst of the energy away before it reaches the optical stack. A slight cant can turn a direct hit into a glance. After the push, the same film can serve as a Whipple shield, riding ahead so the wafer lives in its shadow and sees only what the sail has already broken into smaller, less dangerous fragments. Nothing guarantees safety, so statistics finish the job. Many travelers on slightly different lanes reduce the chance that all of them meet the same unlucky grain. Beam hot spots are inevitable. The art is to keep them from becoming fatal. A phased array can aim for a flat-top profile, but wind and optics add small ripples to any wavefront. The sail must be tolerant of that texture. Surface patterns that spread a narrow spike over a slightly wider patch reduce peak intensity without wasting the beam. Slight beam dithering small, controlled nudges of the spot across the surface during the push averages out residual peaks and lets thermal time constants do the smoothing. The layers below must be chosen for the brief. Violent pulse they will see. They need a damage threshold that is not simply high, but high for a few tens of seconds of duty at the exact color of the beam. Even color matters. A wavelength chosen for low atmospheric absorption and good laser efficiency must also thread the needle of the sail's optical constants. A few nanometers one way or the other can change whether a particular stack stays cool or drinks just enough light to fail. Charging and environment carve their own lines through the problem. Under bright illumination, the photoelectric effect will move charge off the surface. A floating, charged film can tug against itself electrostatically or feel turquoise from ambient fields. Conductive paths are required, but conductivity at optical frequencies invites absorption. The compromise lies in buried meshes and transparent conductors that bleed charge without adding a new way to heat. Before the push, the sail must also live long enough in Earth's near space to deploy without being sandblasted by atomic oxygen or baked by rapid day-night cycling. That argues for a deployment altitude above the worst of the atmosphere, and for films that do not embrittle under ultraviolet light. Radiation darkening has to be measured in months and years, not days. Manufacture and metrology are where physics becomes a checklist. A sail measured in tens of square meters cannot be born in a single chamber. It will be stitched, tiled, or grown in panels with overlaps so subtle the being never notices them. Interferometry reads the shape after every step. Scatterometry checks that the optical constants land where the model promised. Thermal vacuum runs prove the film keeps its calm under the right kind of stress tension. Heat pulses, rapid radiative cooling before anyone trusts it under a beam. The deployment rehearsal is not optional. A sail that opens badly on the ground will open worse in orbit. There is a narrow window between too taut to unfold and too slack to hold shape, and the hardware must find it every time. All of this must be accomplished without forgetting that acceleration will be brutal and brief. 60,000 G is pressure not a crack of a whip, but any feature that concentrates load. An abrupt thickness change a tight corner at a seam, a hard spot where a reinforcement meets a thin. Field becomes a place where failure starts. The safest shapes are smooth, the safest transitions gradual, the safest corrections passive. The sail should want to be centered. The layers should want to stay cool. The film should want to carry load away from wherever it is highest. When the design leans that way, the control system can stay quiet and the beam can do its work. In the end, a light sail is a negotiation between purity and tolerance. Pure reflectivity at the laser's color keeps the film alive. Tolerant thermal paths forgive the few photons that do get in. Pure geometry keeps the sail centered on the beam. Tolerant reinforcement forgives the wrinkles and small wounds that come with deployment and flight. Pure mass discipline keeps acceleration high. Tolerant shielding forgives the thin rain of dust that no one can predict. Mirror, shield, gyroscope, 3 jobs, 1 skin. If the materials and the shape can carry those roles without arguing with each other, the sail will do what it is asked to do in the only moments that count. It will survive the minutes, and it will be there to serve as shade and bumper for the decades that follow. Acceleration has a recipe: a disciplined beam, a reflective sail, a brief profile of rising pressure, and a wafer slips the leash at 1/5 of light speed. Stopping has no such convenience. In vacuum, there is no friction to lean on, no atmosphere to trade speed for heat, and no fuel aboard to fire in reverse. The ship is small on purpose, almost all mirror and mind, and the energy it carries forward is not small at all. For a single gram at roughly 0.2 C, the kinetic energy sits near 1.8 times 10 squared joules, on the order of hundreds of tons of TNT. That ledger must be balanced against something: photons, plasma, or time. Gravity alone, elegant as it is, does not erase energy. It redirects it unless a second agent light or medium joins the act. The simplest sounding idea in early public conversations was to use the planet's gravity and fall into orbit on arrival. Gravity will shape the path, but not slow it to a bound state unless the craft can give energy away during the pass. Without a break, a flyby past a star or a world at 0.2 C is a stone skimming water. A change in direction, not a capture. To become a companion rather than a visitor, the sail must push on something that can take the excess. 3 families of brakes have been studied with that in mind, each trading an honest difficulty for the promise of control. The first is to press on light itself. A reflective sail that rode outbound on a man-made beam can turn and lean against a natural one: the radiation from the destination star. Near a bright photosphere, photon flux rises steeply. A sail that presents its face to that flux and sends photons mostly backward in the star's frame feels a continuous decelerating pressure. The star's gravity helps by curving the trajectory into a close pass where light is most intense. This photogravitational assist behaves like a solar system slingshot rewritten for sails. Come in low over a luminous surface angle of the mirror, so most photons reflect back the way they came and leave with less speed than you brought. In a multiple star system, there is more than one chance. A carefully shaped approach can first harvest braking at Alpha Centauri A, then at B, and only then swing toward Proxima with enough speed removed to let gravity finish the job. A price is design discipline. The sail must survive a steep radiative environment. The aerial density must be low enough that starlight can matter. The geometry must be exact to keep the mirror in the stable portion of its curve, while the pressure grows and relaxes. The prize is deceleration without fuel speed, traded to photons, momentum handed back to the field that supplied it. The second is to press on plasma with magnetic fields. A loop of current can inflate a magnetosphere around a craft. Charged particles in the interstellar medium and later in a star's wind, are turned aside by that field, and their change in momentum becomes drag on the ship. A magsail is the pure version. A superconducting loop deploys, a field blossoms, and the craft begins to feel a break that strengthens as the medium around it grows denser near a star. An electric sail works in a related way, using long charged tethers to create an electric obstacle to the flow of stellar wind ions. Both ideas move in the right direction speed traded to the medium, instead of photons, but both carry severe constraints for Graham-class probes. Field strength, loop size, and power supply all scale harshly. The magnetosphere that would give a 1-gram wafer a meaningful cross-section as 0.2 C is not a toy. Even if a superconducting filament could be spooled to tens or hundreds of meters at destination, the device that feeds it, controls it, and survives its forces must weigh something. And something is exactly what Graham-class budgets refuse. As masses rise to tens or hundreds of grams, magnetic braking becomes less implausible. At a gram, it is still an argument with the scale. The third is to use an external beam, not only to launch, but to slow catch the traveler from behind with light sent years after departure. Flip the sail and reflect the beam forward to sap velocity. In principle, a beam traveling at sea can overtake a ship cruising at 0.2 C. The relative catch-up speed is 0.8 C, and a reflectively tuned sail could turn that overtaking light into deceleration. In practice, the geometry is a punishing teacher. A beamer on Earth would have to stay phase-locked and perfectly pointed across light years and decades, shining through weather and orbital clutter, and the craft would have to keep a forward-facing mirror, thermally safe while it throws energy forward into empty space. A beamer deployed far from Earth, perhaps in solar orbit, and slowly accelerated outward to trail the probe, softens some of those constraints, but then the infrastructure problem moves with it. None of this is forbidden by physics. Much of it is hostile to budgets and schedules. If a sail leans on photons aggressively enough, stopping becomes a sequence rather than an event. The approach must be shallower than a straight line toward the target planet. A distant, precise aim point near the photosphere of a bright primary maximizes the decelerating pressure. The sail's curve keeps it stable as the beam from the star pushes backward on its motion. The outbound leg from that first pass is not outbound in defeat. It is outbound with less speed, bent toward a second primary if one exists, and then toward the red dwarf where a candidate world may circle. Only after that ladder of light has taken its share does gravity offer a bound path that is more than a metaphor. A planet's atmosphere, if present, adds another possibility. Skimming a high exosphere with the sail turned into a shield, letting atomic drag shave the last meters per second that keep a trajectory open. That step is the most conditional of all, relying on unknown atmospheres and perfect aim, and it is the only one in the set that courts heat rather than avoids it. The program's sober line remains: plan for a flyby, and treat any deeper capture as a bonus achieved by a design that discovered it could break. The notion sometimes attached to Stephen Hawking's name in popular summaries that You decelerate by placing the craft into a planet's orbit, is pointing at this end state without spelling out the means. Orbit is not a method. It is the result after energy has been given away. The method is the transfer itself. Photons and plasma are the two honest banks that will accept that payment. Gravity is the corridor that walks the craft to the teller. If the transfer is successful, orbit follows naturally. Once the kinetic energy has been lowered below the threshold for escape, a world or a star does not need to be tricked into holding the traveler. It holds it by default. An attempt to stop must also respect what cannot be scaled down. A sail cannot be perfectly reflective at a star's full spectrum. Near periapsis, a fraction of the light will always be absorbed, and the thermal model must live with that fraction. A magnet sail cannot conjure a strong field without a loop, and a loop cannot be a rumor. It must be wire, deployer, and current, all of them real. An external beamer cannot be in principle when aircraft and satellites and clouds live between ground and sky. It must be governed, shuttered, and aimed in a world where safety and law share the air. These are not complaints. They are the shape of the problem. Every path to stopping, even partially, carries a penalty in time. A photogravitational sequence through a multiple star system will add years to a mission that was already measured in decades. A magsail begins to bite only when the medium thickens near a star, which means the craft must overshoot the first temptation to dive and accept a gradual break instead of a dramatic one. A trailing beamer can only catch up on a schedule set by light speed and geometry. None of that makes capture unworthy. It simply puts it in the same column as every other hard step in the architecture. Possible, conditional, and expensive in the currency of patience. Stopping in a vacuum is therefore not a single trick, but a discipline. Energy leaves the ledger by pushing on fields electromagnetic or plasma, while gravity supplies curves that put the sail where those fields are strongest. At the smallest masses, leaning on starlight is the cleanest option because it asks for what the sail already is. At larger masses, magnetic parachutes begin to matter. At any mass, a dedicated beamer at the destination would turn braking from maybe into planned, though it would also turn a research program into a civilizational project. Flyby remains the baseline because it is honest about what can be promised now. Capture remains a goal because curiosity is not content with a glance if a longer look can be earned. If conditions align a reflective skin that keeps its cool, a geometry that keeps balance near a star, a path that threads between primary speed can be traded to light until gravity's hand is enough to hold. And if the craft cannot be caught, it can still learn. A fast pass yields images, spectra, and light curves that no telescope at home can match. A stopped craft yields weather, seasons, and surface changes written over years. Both payoffs begin with the same acceptance. In a vacuum, nothing slows you unless you build a way to give your motion to something else, and then aim for the places where that something is strong. Power has to be earned gram by gram. A wafer that weighs about a paperclip cannot hide a power plant, and the dark between stars does not hand out electricity. Two families of ideas keep returning to the table. One is nuclear in miniature, radioisotopes that shed heat continuously, and ferroelectrics that skim a fraction as electricity. The other is sunlight harvested, while it is still bright ultra-thin photovoltaics that charge storage before the craft leaves the inner system. Then a years-long budget that spends that charge in careful bursts. Both are honest, both run into scale. A conventional RTG starts with heat. Plutonium-238, for example, produces roughly half a watt of thermal power per gram strong and steady. The converter that turns that heat into electricity is not ideal. Efficiencies live in single digits. That means a gram of isotope yields, at best, a few tens of milliwatts of electrical power, and the converter and containment weigh far more than the fuel itself. Shrinking the assembly to fit a gram-class spacecraft leaves you with a paradox. The device that could make watts cannot be made small enough to fly. There are gentler nuclear options, photovoltaics that turn the soft rain of emitted electrons into trickles of current, or diamond devices that sip charge from long-lived isotopes. They have the virtue of lasting decades, but their output is measured in microwatts to milliwatts. They keep time and memory alive. They do not power cameras and transmitters at full voice. The solar route accepts that energy will be plentiful early and scarce later. Ultra-thin photovoltaics spread across the sail or across a separate film can harvest sunlight near home and store it in solid-state batteries or supercapacitors made to survive launch G-loads and long, cold naps. The arithmetic is unforgiving, but manageable if the duty cycle is right. Housekeeping sleeps for months. Navigation wakes rarely, reads a star field, and sleeps again. Memory is checked and scrubbed on a slow cadence. Most of what the craft will ever spend is reserved for 2 brief seasons: the minutes of sensing during the flyby and the long, patient days of transmission that follow. A 1-watt budget becomes a way to think, not a number to hold every second. Average power between stars can be tens of microwatts, and the craft will be content. A watt is the kind of burst you want in hand for the encounter short exposures and fast readouts, and for the first hours of the downlink when geometry is best. That watt can be saved in months of quiet and then spent in minutes of use. The design that survives is the design that wastes nothing. Detectors that can idle cold by radiation to space instead of heavy cryogenics logic that sips in sub-threshold modes. Clocks that wake only to set milestones and then go still again. Communicating across 4.24 light years is not a shout. It is a whisper that refuses to give up. Free space loss dominates everything. A small antenna flinging radio across that distance spreads power so thin that even the largest dishes collect almost nothing. The way around that is not brute force aboard the craft. It is coherence on Earth. Many ears can act like one if they are time-kept and combined well. A global array of receivers' radio dishes, linked by atomic clocks and careful calibration, can add signals coherently so that what is below the noise in any one ear stands above it in the sum. If true coherence proves fragile at these scales, power can still add non-coherently. The gain grows only with the square root of the number of stations, but a very large number of small receivers still moves the needle. The concept scales from professional networks, deep space network sites, next-generation radio arrays, to millions of modest instruments, if synchronization and calibration are handled with discipline. The sky does not care whether the ear is one dish or many. It cares that phase and timing are kept. There are also ways to give a coin-sized transmitter a larger voice without asking it to carry mass it cannot afford. The sail, if retained after launch, can double as an antenna. At radio frequencies, a reflective sheet meters across can be shaped into a shallow dish or patterned to act as a phased surface, tightening the beam and buying precious gain without adding separate structure. At optical wavelengths, a tiny laser diode cannot throw many photons, but a reflective aperture measured in meters can collimate what it has into a beam, narrow enough that an Earth-based telescope sees more than starlight and noise. The numbers are still tight photon budgets at optical frequencies, punish small transmitters, but narrow beams and long integrations make bits appear where none seemed possible. Encoding and cadence finish the job. The data do not leave as raw images. They leave as carefully coded packets with redundancy that survives gaps. The order puts the most precious pieces first, brief image summaries. Spectra collapsed into a few diagnostic bands, housekeeping that proves context and repeats them until Earth acknowledges receipt or until the budget runs dry. Between repeats, the transmitter can go dark and let storage recover. The receiving side mirrors the patience. Correlators integrate over minutes, hours, and days. Clocks hold phase. Software excises false positives from terrestrial interference and recomposes a picture a few photons at a time. A third path sometimes appears in sketches. Power beaming from Earth for the downlink itself. A faint, well-aimed laser that the sail or a small photovoltaic patch can harvest at the right moment to energize a brighter transmitter burst. In principle, the geometry works light at sea, overtakes a craft at 0.2 C, and schedules can be written years in advance. In practice, the pointing and safety constraints are severe, and the harvested power after light years of spread is small. If such a scheme contributes, it will be as a supplement timed for the most favorable windows, not as the backbone of the plan. None of these solutions is generous. Together, they are sufficient. A ground-class traveler can live for decades on microwatts if it sleeps like a stone and wakes like a cat. Brief, alert, and exact. Storage that holds its charge and endures radiation can release that stored watt when seeing matters. An Earth that listens as one instrument, whether through a few giant dishes, kept in step or through a web of countless small ears, can hear a transmitter that would be mute to any single sight. The physics of distance is not softened by optimism, but it does leave spaces for craft and patience to work. What that means on the ground is a mirror image of the sail's discipline. Energy that powers the beamer is banked in grid-scale storage and released in minutes. Energy that powers reception is spread across continents and used for years. Governance keeps beams inside safe corridors. Calibration keeps ears in phase. On the craft, the ledger stays simple. Store when light is plentiful. Spend when knowledge is close. If a single shard of image, or a narrow line in a spectrum returns from the far side of the long room, it will be because watts were treated like treasure, and because a planet learned to listen to itself as if it were one machine. Catching a 1-gram probe as whisper from 4.24 light years away is not so different from listening for someone else. The same antennas, clocks, and discipline that lift a faint signal from our traveler will also make a better ear for technosignatures. The overlap is practical first. A global net of receivers, large dishes, and many small stations, kept in time by precise clocks, can add their voltages together coherently, so what is buried in the noise at each site stands above it in the sum. When coherence cannot be held, powers still add non-coherently and help, just more slowly. Either way, the act of making many ears behave like one becomes a standing capability, and once it exists, it spends most nights listening to the universe, whether a probe is speaking or not. The character of the signal sets the rules for how to listen. At cruise near 1/5 of light speed, the probe's transmissions will be spread and shifted by motion. Radial velocity introduces a Doppler offset that can reach tens of percent if geometry lines up directly. The Earth's own spin and orbit add smaller, periodic swings. Plasma along the path can smear and scintillate. The receiver corrects what it can, basebanding the signal into a narrow window, applying barycentric corrections to remove Earth's motion, searching a family of drift rates rather than a single tone. Coherent integration over long spans is the lifeline stacking seconds into minutes into hours, because a true signal will add like a straight column while noise wanders sideways and cancels itself. False positives demand a ritual, and it is the same ritual that gives SETI credibility. A candidate that lightens the heart in one beam must vanish when the array nods off target by a small angle. It must appear at multiple, widely separated sites within the bound set by the speed of light. It must drift in frequency in a way that matches the sky's mechanics rather than a local oscillator as temper. It must survive polarization tests, notch filters that carve out known terrestrial bands, and cross-checks against databases of satellites and aircraft. Only then is it a detection worth the next step, which is repetition on a new night. The discipline is dull by design. It protects against the human tendency to fall in love with the first clean line on a waterfall plot. Modulation choices link interstellar comms and technosignatures at a deeper level. A narrowband carrier, a single tone just hertz or less wide, minimizes transmitter power for detection and is easy to separate from natural spectra, which are broad. That is why narrowband has long been the archetypal SETI beacon, and why a wafer-class probe will likely pin a small fraction of its budget to a stubborn ultra-narrow pilot tone that the Earth array can lock onto for hours. But data rides better on something wider phase modulated subcarriers or a gentle, spread spectrum that trades instant detectability for resilience, coding gain, and the ability to hide under noise where interference is busy. Receivers prepared for both worlds search hierarchically, first for an improbably narrow spike with a plausible drift, then for structured sidebands or autocorrelation peaks around that spike, then for broadband patterns that repeat with the machine's patience. The same tools that peel telemetry off a Graham-class flyby will peel patterns out of a sky full of possibilities. Optical strategies belong in the kit as well. A tiny radio can be heard if enough small dishes add up, but a tiny laser, tightly collimated, concentrates each photon more fiercely. Optical SETI hunts for either continuous, extremely narrow lines or for nanosecond pulses that stand above the shot noise of starlight. The infrastructure that stabilizes a phased radio array timing, coincidence, and VIDOs has an optical cousin. Fast photodetectors at separated observatories watching the same star, accepting only events that arrive in coincidence with the right dispersion and delay. For the probe, an optical downlink may be impractical in power, but for SETI, it remains attractive because nature rarely makes nanosecond pulses. If the ground learns to catch our own, it will be better at catching anyone's. Beamforming is the quiet hero behind both tasks. When many antennas or tiles are calibrated into a synthetic aperture, software can form multiple simultaneous beams, one on target, others on nearby sky for VIDO, still others scanning for surprises. That makes on-off testing cheap. It also turns spare capacity into survey time. A network patient enough to wait 4 years for a flyby's first bits will not sit idle. It will be a continuous watcher, and its archived basebands will be a library others can reanalyze with fresh algorithms. In that sense, building a Starshot-class ear is also building a commons for the search for intelligence. Rejection of interference improves when the array behaves like a scientist rather than a single instrument. Near-field tests does the signal focus when we synthetically focus at infinity, or does it smear like something nearby? Separate emissions in the next county from emissions at the next star. Time difference of arrival across continents triangulates uninvited transmitters that bounce off the ionosphere. Polarization scrubs out radar. Known orbital elements carve predictable scars into the spectrum where satellites live. Those scars can be masked by default. Nothing is perfect, but careful habits make the remaining candidate list small and honest. The shape of a good detection carries lessons both ways. A genuine artificial signal will show intent either in economy or in generosity. Economy looks like a razor-thin carrier drifting exactly as the kinematics predict, perhaps with a prime number cadence or a simple keying that wastes no power. Generosity looks like redundancy and error-correcting codes that are hard to invent by accident and easy to verify across days. Either quality is enough to drive confidence upward. The most precious virtue is repeatability. If a signal can be scheduled, it can be studied. If it can be studied, it joins science rather than rumor. There is a social mirror to the hardware. Open logs, reproducible pipelines, and public data releases keep confidence high and make it possible for independent groups to confirm or refute claims quickly. A citizen layer of small receivers' modest dishes, even backyard arrays locked to common timing, can participate in non-coherent sums and in vetoes of local interference. The line between deep space network and global community radio telescope blurs in a productive way when plans are public and formats are standard. In the end, the most practical implication is simple. Learning to hear our own faintest transmission makes us better at hearing anything faint and deliberate. A network that can follow a drifting red-shifted whisper from a gram of silicon will be comfortable with the flavors of narrowband and spread spectrum, with the personalities of laser and radio, with the quirks of scintillation and the patience of long integration. If no one else is speaking, that network will still return a trove of natural signals pulsars, masers, plasma storms that sharpen our models. If someone is speaking, it will know how to ask the right questions quickly. Does it repeat? Does it drift as it should? Does it vanish when we look away? And does it come back on a night no human chose? Those questions are the gate through which any good claim must pass, whether the transmitter is a wafer we launched or a neighbor we have yet to meet. A beam powerful enough to throw a sail to interstellar speed turns the ground into part of the spacecraft. From the moment a phased array points skyward, the site is no longer only an observatory or a power plant. It is a piece of critical infrastructure whose behavior must be as predictable as an airport and as transparent as a national lab. The first challenge is the air itself. Turbulence blurs and tilts wavefronts. Humidity and aerosols drink light. A high, dry plateau helps, but location is not cure. Adaptive optics must sense the shimmer and cancel it in real time, and the array must decide, second by second, whether the wavefront is flat enough to proceed. When it is not, the system must go dark on its own. No mission is worth a bad night of seeing. Safety is the next unmoving pillar. A multi-gigawatt column does not share airspace. Corridors above the array have to be cleared the way runways are cleared with live feeds from civil aviation and space traffic networks. Automatic shutters that fail closed, and geofences that make it physically hard to laze outside a defined cone. Satellites and debris cross those cones every minute. A control loop that cannot see and react to an unexpected track is not a control loop fit for use. The rules belong in hardware as much as software. Interlocks that cut power when any guardrail is touched, shutters that default to dark, and watchdogs that cannot be overridden by a single operator. Logs must be immutable. When the sky says no, the instrument must obey without debate. The beam's relationship with orbit is complicated. A well-behaved array still shares a planet with thousands of satellites and countless shards of debris. Even brief illumination can dazzle optical sensors. Long illumination can heat or stress a surface. Steering laws and scheduling must be coordinated with space traffic authorities, and the array should expect to accept no-go windows to protect passing hardware. The carrier craft that releases each sail must follow a debris-conscious life cycle of its own, controlled deorbit or graveyard disposal. Passivated tanks tracked fragments if anything fails. A system that helps explore the sky cannot be one more hazard to it. Energy demand speaks with plain numbers. Peak power lives in the tens to hundreds of gigawatts for a few minutes, with total energy per firing landing in the territory of many terajoules. The grid will not appreciate a sudden gulp of that size, so storage becomes part of the architecture. Banks that charge slowly over hours or days and empty quickly for those minutes of work. Conversion and cooling waste their share. Water and heat must be managed in closed loops that do not scar the local environment. The site needs the footprint of a small industrial campus and the discipline of a large one. High voltage yards, thermal plants, battery halls or flyheels, redundant fiber, and physical security that protects without turning a research facility into a secret. Costs obey the same scale as national telescopes and colliders. Land, storage, lasers, optics, cooling, power interconnects, safety systems, ground receivers. The total belongs with the world's largest scientific instruments. That cost argues for shared ownership. A project that invites many nations to build, audit, and schedule the array is easier to trust than a project owned quietly by one. Governance will matter as much as glass and gallium. A charter that names safety first, a board with scientific and public representation, independent review that can stop operations, and a habit of publishing schedules, logs, and environmental reports so the outside world does not have to guess. Dual-use concerns arrive with the hardware, not after it. A coherent, steerable, high-power laser array looks to a strategist like more than a science instrument. Even if the beam is never pointed at the horizon, even if its profile is shaped to be useless in air, it can still dazzle sensors in orbit, test missile warning systems, or be mistaken for a weapon trial by a rival watching from afar. Export controls and non-proliferation regimes will take an interest. Components that make Starshot possible: high-brightness laser diodes, adaptive optics, phase-stable timing, high-density storage appear on lists that require licenses to move across borders. The only antidote to suspicion is daylight. Publish specifications that cap what the array can do, treaties or memoranda that forbid certain pointings or power levels, and invitations to international inspectors who can verify those limits on site. Law and policy will have to grow around the beam. Airspace is governed nationally. Orbit is shared. The atmosphere sits between them, and no single agency owns the column that connects ground to deep space. A workable scheme stitches civil aviation, space traffic management, environmental regulators, and scientific operators into one loop. Flight corridors close automatically when the array is armed. Satellite operators receive machine-readable schedules and can return hold votes that the array must honor. Environmental monitors oversee water use, thermal plumes, and wildlife impact. And all of it sits under a license that can be suspended if logs and behavior part company. None of this is glamour. All of it is legitimacy. There are softer risks with hard consequences. Weather is not only turbulence, it is lightning. A facility this large becomes a preferred path unless it is designed otherwise. Cybersecurity is not a checkbox. A control system that can be driven from a network by anyone other than its own operators is a liability to the sky. Community acceptance is not a press conference. It is a decade of steady, honest presence. Jobs for local people, contracts for local firms. Noise and light kept to what was promised, and real authority for neighbors who say, "Not today," when the wind is wrong or the migratory path is full. International politics will test patience more than physics will. An array built in one nation and pointed over another will draw criticism the day it lights. An array built by a coalition will move slowly because coalitions do. Either way, the project will need a habit of proving what it is not. It is not an anti-satellite system. The pointing and power limits enforce that. It is not a surveillance tool. Its sensors are almost entirely inward-looking. It is not a first-strike machine. Its shutters close as soon as the sky becomes impure. These statements cannot be marketing. They have to be enforceable rules, with inspectors able to read the same logs the operators read and to cut power if trust wavers. The longer arc is environmental and social license. A high-altitude site is precious for reasons that have nothing to do with lasers. Fragile ecosystems, scarce water, cultural landscapes. An instrument that needs clear air can live where astronomers live now, but it must accept the same responsibilities. Minimal permanent light, careful water cycles, quiet nights, footprints that shrink as technology improves. If a site hosts indigenous communities or sacred lands, the agreements cannot be symbolic. Shared governance and direct benefit must be real, and the right to say no must exist and be honored. If not, engineering will proceed and politics will undo it. Finally, there is the matter of timing and narrative. A beam that lights for minutes and sleeps for months will always be judged by those minutes. Misfires and near misses will count more than 1,000 quiet nights of compliance. The project's answer has to be steady humility. Fault trees published, incidents dissected in public, lessons turned into hardware changes, and no attempt to hide the risk behind grand language. Engineering wins credibility when it owns its failures. Governance wins credibility when it can pause operations without permission from the very people being paused. Building the array will remain a technical triumph-phased light through moving air, wavefronts held flat across acres, energy banked and released like a sprint, and yet the beam will not fire unless law, policy, and trust fire with it. The sail must reflect, the array must obey, the institution must be believed. That is what engineering is only half the story means here. Materials and control will push the frontier for minutes. Politics and patience will hold the door open for years. Only together do they make a path where a column of light can rise from one world without alarming the others that share the sky. So, what happened? Current status and what's next? The rumor around an audacious project is that it either died in the headlines or leapt straight to history. The truth for Breakthrough Starshot sits between those poles. It has left the realm of slogans and moved into the long, workmanlike years of laboratory progress, Pathfinder missions, and hard questions about power, safety, and law. The core aim is unchanged push gram-scale craft to a significant fraction of light speed with a brief, disciplined burst of photons, and the program remains framed explicitly as research and development rather than a dated launch commitment. The official posture is to prove the enabling pieces first, from materials and beam control to communications and governance, and only then contemplate a first attempt toward Alpha Centauri within a human generation. On the materials front, the last seasons have been about turning models into measurements. At Caltech, the sail team took an early cautious step that mattered more than its modest scale implied. They put a tiny tethered light sail under a laser and measured the push directly in a setup built to read the delicate balance between optical pressure, thermal behavior, and mechanical calm. It was not a free-flying sprint. It was a careful first grip on the force that the mission depends on, documented in a peer-reviewed paper and a university report that set down methods others can repeat. The destination was not speed, but understanding how a metasurface warms, how it steadies, how a beam profile translates to motion, and it marked the shift from slide decks to data. Theory has stayed ahead of hardware, as it should, sketching the contours of sails that prefer stability rather than demand it. Work on flexible radiation pressure-driven metasurfaces showed how geometry and optical phase could be tuned so a sail rides a beam the way a ball settles in a shallow bowl, turning hot spots and tilts into restoring forces instead of failure modes. More recently, designs for photonic crystal mirrors with pentagonal tilings explored how to scale reflectors while keeping absorption. Vanishingly small and thermal paths generous an approach that points toward large manufacturable sheets with the 5/9 reflectivity the beamer will require. These papers are not blueprints, but they are maps. Each narrows the space of shapes and stacks that can survive minutes of fury without tearing or cooking. Meanwhile, a different family of sails has been busy where sunlight itself is the engine. NASA's Advanced Composite Solar Sail System launched in 2024, unpacked an 80 square meter film in orbit, and began the slow, careful work of showing that very large, very light structures can be stowed, deployed, and steered. It is not Starshot, no lasers, no sprint, but it is the same language of booms, folds, strain relief, and attitude control, and it feeds the same skill set. NASA's own notes point to follow-on booms sized for sails hundreds to thousands of square meters, the scale where photon pressure, whether from the sun or a beam, starts to add up. Even with real-world hiccups after deployment, the demonstration moved a crucial line from proposed to flown. The beam itself remains a discipline more than a device. Coherent combination, many modest lasers acting as one, is no longer an abstraction. It is a field with testbeds and tiles, with atmospheric propagation experiments and control loops that try to hold a wavefront flat through moving air. Starshot's own laser roadmap has been published in outline, and technical papers have sketched the photon engine as needs power, phasing, cooling, and safety gates, while parallel efforts in academia investigate Earth-to-space transmission, beam steering, and array coherence as standalone problems that still add up to the same instrument. No one has built a kilometer-scale, 100-gigawatt array. Many groups are learning how to keep dozens and hundreds of emitters in step without losing their calm when the wind changes. Progress is not only in papers. The program has stayed visible on Scientific Stages Breakthrough's annual discuss meetings, interstellar symposia, invited keynotes with the sail team, and collaborators keep showing not just animations, but measurements, failure modes, and next gates. In Montreal, at the Interstellar Research Group's gathering, for example, Starshot's lead on sails distilled the posture to its essentials, defined the problem precisely, developed the pieces faithfully, and do not confuse enthusiasm with readiness. It is the tone of a long project that knows it must earn each rung rather than jump the ladder. Timelines, when they appear, are cautious by design. Public summaries still echo a within a generation aspiration, and sometimes cite back-of-envelope cost and date sketches on the order of billions in total infrastructure. And, in optimistic scenarios, a first flight sometime in the 2030s. But the program itself has avoided promising a day on the calendar. The order of work is clearer than the year. Prove sails that reflect nearly everything at the laser's color and shed the rest as heat. Prove beam riding stability that does not need propellant to behave. Prove coherent, steerable light through real air with shutters that fail dark and governance that stands up in public. And prove a receiver network that can hear a whisper from 4 light years away. Only then talk about lighting the column for minutes. What comes next, in practical terms, looks like a sequence that repeats more than it escalates. In the lab, sails will leave their tethers and ride free on short paths inside vacuum lines, so stability can be measured without the help of a frame. Damage threshold testing will get harsher and more honest higher flux, longer duty, tighter beams until the surviving stacks and shapes become the default rather than the exception. On the beamer side, phased array tiles will grow in number and in outdoor hours. Adaptive optics will be trained against real messy seeing, and safety logic will be exercised until no is as routine as go. In orbit, small pathfinders could try beam riding at modest acceleration, not to set records, but to tune guidance and control in the environment that matters. And on the ground, the ear will take form. A handful of large dishes phasing up with a web of smaller. Receivers practicing exactly the kind of long coherent integrations that will one day pull bits from noise. None of these steps is a headline. Together they are a staircase. The other half of what's next is not engineering at all. A multi-gigawatt array on Earth needs a license born of law and trust, not just lab reports. Airspace authorities and space traffic managers must be in the loop. Shutters must default to dark. Logs must be immutably recorded and auditable. Environmental footprints must be honest and contained. Export controls and dual-use worries will shadow every procurement. The most realistic path forward is international on purpose, with shared ownership and inspection, so the instrument is seen as a telescope that happens to push rather than a push that happens to look. That kind of governance takes longer than a build. It also outlives a build. So has the dream stalled? The laboratory record suggests otherwise. It has become what serious dreams become. A list of measured problems being worked in parallel by groups willing to publish what breaks as well as what holds. A tiny sail lifting under a beam in a Caltech lab is a small scene, but it is the scene that had to come next. A gleaming square of film opening to tens of square meters in orbit is a different scene, but it is the same language of mass, strain, and light. An array of lasers holding phase through bad air is not a spectacle. It is the proof that a column can stand long enough to matter. The destination hasn't moved. The route there is just becoming visible in the sort of steps that do not trend on their own. If the near-term years keep their pace, expect more of the same and a little braver. Free-flying sails and vacuum lines. On-sky beam tests that last longer. Orbital rehearsals that replace sunlight with a modest ground beam. And somewhere down that line, a first sprint that is not yet interstellar, but is unmistakably starshot in posture and intent. When the minute finally comes to light the full column, the public moment will be brief by necessity. The quiet afterward will be the point. And if 2 decades later, a tight time-kept array on Earth lifts a handful of bits from the noise and turns them back into a tiny, fast view of another sun's neighborhood, the patient record that led, it will be the answer to the question of what happened in the meantime. The years went to making light into an engine and making listening into a certainty. Light is the first technology we ever mastered, and the last frontier we've barely touched. Starshot turns it into both engine and message. A gram of silicon riding a mirror, pushed for minutes by a man-made star and heard years later by a planet-sized ear, if that works even once. Exploration changes character. Propulsion decoupled from propellant, materials that shrug at heat, phased arrays that write wavefronts through air, receiver networks that make a whole world listen as one. Power beaming, optical comms, SETI. Even how we govern shared skies, all of it shifts when light becomes a tool we can aim, hold, and trust. So the question to fall asleep with is simple and enormous. When the first clean whisper arrives from 4 light years away, a thin crescent, a taut spectrum, a line that means air, what else suddenly becomes thinkable? If a paperclip of intention can keep an appointment with another sun, what limits were real and which were just habits? Let that possibility keep you warm tonight. See you, Space Cowboy. Sleep well and good night.